Concentration of C raised to the power C, which is the stoichiometric coefficient of that, D to the power D, same way divided by A to the power A into B to the power B. This is the equation for Kp, which is equal to K1 by K2, or else Pc raised to C into Pd raised to D divided by Pa raised to A into Pb raised to B. The difference in number of moles of products and reactants, when it is equal to 0, what happens? Kp and Kc will be equal. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in the last session, we studied about equilibrium of chemical reactions, right? That is chemical equilibria, and then the characteristics of chemical equilibrium as well as different types of chemical equilibrium, right? And what is law of mass action, and few examples and numericals based on that also we discussed in last session. So in today's session, we are going to study about derivation of Kp expression for gaseous reversible homogeneous reaction and relationship between Kp and Kc. Okay, and applications of equilibrium constant as well as the relationship between equilibrium constant, reaction quotient and Gibbs energy. So this Gibbs energy, what it is, you have already studied in thermodynamics chapter. Reaction quotient will be new for you. Equilibrium constant also we have discussed in the last session. So the relationship between all these three we are going to discuss. So in today's session, majorly we are going to focus on Kp. Now, Kc is already a known thing, that is, it is equilibrium constant, right? Now, let's understand how to derive an equation for Kp. Now, that means Kc, why we were using Kc? We were defining equilibrium constant in terms of concentration, right? How do you write it? Kc will be equal to C to the power C into D to the power D divided by A to the power A into B to the power B, where C and D were the products and B were the reactants, and it is mentioned in the brackets to show that it's their molar concentration, right? So concentration of C raised to the power C, which is the stoichiometric coefficient of that, D to the power D, same way divided by A to the power A into B to the power B. So this is called as the equilibrium constant in terms of concentration. Now, as you can see, we are going to derive an expression for Kp, that will be in terms of pressure now. So let's see, let's take a general equation AA plus BB giving CC plus DD. So small letter A, B, C and D are the stoichiometric coefficients or the number of moles, and capital AB are the reactants and C and D are the products, right? So consider a gaseous reversible reaction. It is conducted in a closed vessel at constant temperature, right? And let Pa, Pb, Pc and Pd be the partial pressure of the reactants and products. Okay, so we are going to talk or we are going to discuss in terms of pressure now. Okay, so Pa will be the partial pressure of A, that is the pressure contributed by reactant A. Then Pb will be the pressure of partial pressure of B, Pc will be the partial pressure of C, Pd will be the partial pressure of D, and V1 and V2 be the velocity of forward reaction and backward reaction. So the velocity with which the forward reaction is taking place, let that be V1, and the velocity with which backward reaction is taking place, let that be V2. Now, applying the law of mass action to the forward reaction. So, law of mass action we have already studied in the last session, right? So, V1, that is the rate or the speed with which. Okay, here we are discussing in terms of velocity. So, what did we study? The law of mass action, the rate of the forward reaction or the rate of the reaction will be directly proportional to the product of the concentration of the reactants raised to the power which is equal to their stoichiometric coefficients, right? So first we are going to discuss for the forward reaction, which is the forward reaction AA plus BB giving CC plus DD. That is a forward reaction, right? So in the forward reaction, which are the reactants A and B, right? So now we are going to write in terms of pressure, right? So you can see here V1, that is velocity of the forward reaction, will be directly proportional to pressure, partial pressure of A raised to the power A, which is a stoichiometric coefficient, and PB raised to the power B, right? Now, to remove the proportionality, we introduce a constant which is K1. So, V1 will be equal to K1 into PA raised to A into PB raised to B. So, I hope it is clear, where K1 is the velocity constant for the forward reaction. Now, we are going to apply the law of mass action for the backward reaction. Now, which is the backward reaction? CC plus DD giving AA plus BB. So, now in that case, which will be the reactants? Yes, it will be C and D. Now, those are the reactants. So, now we are going to write in terms of partial pressures of C and D, right? So, V2 V2 is the velocity of the backward reaction, right? So V2 is directly proportional to Pc raised to C into Pd raised to D. Okay. Now again, to remove the proportionality, we introduce the constant which is K2. So V2 will be equal to K2 into Pc raised to C into Pd raised to D. Right. Now, where K2 is the velocity constant of the backward reaction. Now, at equilibrium, what did we study? The rate of forward reaction and the rate of backward reaction will be equal. So, what does that mean? V1 will be equal to V2. So, already we have found the equation for V1 as well as V2. So, now we are going to equate these two, right? So, V1 will be equal to V2. That means what was V1? K1 into Pa raised to A into Pb raised to V. What was V2? K2 into Pc raised to C into Pd raised to D. Now what we are going to do is we are just going to rearrange this equation. So K1 by K2. Okay. K1 is already here. We are taking the K2 to this side. Okay. So if we are taking it to other side of the equation, it becomes the denominator, right? So K1 by K2 will be equal to, so this much part will remain there itself and this part we are going to take it to the other side. So it will become the denominator. So it will be Pc raised to C into Pd raised to D divided by Pa raised to A into Pb raised to B. Right. Now, what is K1 by K2? That will be equal to your Kp. Right. Okay. Earlier it was Kc when it was in terms of concentration. Now it is in terms of pressure. So it is Kp. So Kp will be equal to K1 by K2. That is velocity constant for forward reaction divided by velocity constant for backward reaction, which is equal to the product of partial pressures of the products raised to their stoichiometric coefficients divided by the product of the partial pressure of the reactants raised to the power which is equal to their stoichiometric coefficient. So I hope it is clear. So equilibrium constant is the ratio of product of partial pressures of products to the product of partial pressure of the reactants raised to the power of respective number of moles. Okay, respective number of moles, also you can say it as the stoichiometric coefficient. So this is the equation for Kp, which is equal to K1 by K2, or else Pc raised to C into Pd raised to D divided by Pa raised to A into Pb raised to B. So I hope the equation for Kp is clear for you. Now we are going to find out what is the relationship between Kp and Kc. Okay, so this is a very important equation, that is Kp is equal to Kc into Rt raised to delta Ng. Okay, so what is Kp? Equilibrium constant in terms of pressure, right? Partial pressures. Kc, equilibrium constant in terms of concentration. Now what is R? R is universal gas constant. What is T? T is temperature. And what is this? Delta Ng. Now delta N means it is the difference in the number of moles of products minus reactants. That means it is the number of moles of gaseous products minus the number of moles of gaseous reactants. So as you can see here, it's not just written delta N, it is written delta Ng. It is only the number of moles of reactants and products which are in gaseous state we are going to consider. For example, if let's take N2 plus H2 giving NH3. So if we are going to balance this, it becomes 3H2 and 2NH3. Right. So now how do we calculate delta Ng in this case? We have to substitute in this equation Kp is equal to Kc into Rt raised to delta Ng. So how do we calculate this delta Ng is the question. So it is the number of moles of products in gaseous phase minus number of moles of reactants in gaseous phase. So nitrogen, hydrogen and ammonia, all of them are in gaseous phase. Right. So delta Ng, how do you calculate? It will be equal to 2. Number of moles of products is 2, right? Minus number of moles of reactants, it is 3 plus 1, right? 3 plus 1, that is 4. So it will be equal to minus 2. So I hope it is clear. So this is how you have to calculate delta Ng value. So this equation is very, very important. It's a relationship between Kp and Kc. Kp equal to Kc into Rt raised to delta Ng. Okay. So now moving on, write the relationship between Kp and Kc for the following reactions. So the reaction is already given. This reaction we have already just discussed now. So as you can see here, delta Ng we calculated 2 minus 4 which is equal to minus 2. Kp is equal to Kc into Rt raised to delta Ng. So here in delta Ng we are going to substitute the value minus 2, right? So Kp will be equal to Kc into Rt raised to minus 2, Rt raised to minus 2. So raised to minus 2 means we can write it in the denominator as well as Kp is equal to Kc raised to Rt raised to minus 2. So what does that indicate? Kp will be less than Kc. Now let's take the example. PCl5 giving PCl3 and Cl2, which is a reversible reaction. So again let's calculate delta Ng, right? So all of them are in gaseous phase. So all of them we are supposed to consider, right? So the number of moles of products will be here 1 and here 1. So that is 2. Now number of moles of reactants, it is just 1, right? So 2 minus 1 will be equal to 1. Now Kp is equal to Kc into Rt raised to delta Ng. In place of delta Ng, we are going to substitute 1. So Rt raised to 1 will be equal to Rt itself, right? Anything raised to 1 is that value itself. So Kp is equal to Kc into Rt. So what happens? It becomes Kp is greater than Kc. Okay, why? Kc into Rt, this into Rt will be equal to Kp, right? So of course Kp will be greater than Kc. Now the third condition we can see 2Hi giving H2 plus I2. Okay, it's a balanced chemical equation. Again, let's calculate delta Ng. Here number of moles of products, it is 1 and 1 here, right? So that is 2. Now number of moles of reactants, it is just 2. So 2 minus 2 will be equal to 0. So again we are going to consider the equation Kp is equal to Kc into Rt raised to delta Ng. Now what is delta Ng? It is 0. Anything raised to 0 will be 1, right? So this term will become 1. So what happens? Kp will be equal to Kc into Rt raised to 0. So that is equal to 1 and it becomes Kp will be equal to Kc. So when the number of moles is equal to, that is the delta Ng value, the difference in number of moles of products and reactants, when it is equal to 0, what happens? Kp and Kc will be equal. Right. So I hope it is clear. Now moving on to the next one, the relationship between equilibrium constants for a general reaction and its multiples. So we know that for a particular reaction, the equilibrium constant value will be a constant. That means that, let's consider this general equation AA plus BB giving CC plus DD. It's a reversible reaction and it's given that the equilibrium constant for this reaction is Kc. Now what we are going to do is, for the forward reaction we are considering it as Kc. That is this one, A and B are combining and forming C and D. That's a forward reaction for which the equilibrium constant is Kc. Now we are considering for the backward reaction, that is C and D will combine to form A and B, which is the backward reaction. Now what will be the equilibrium constant? We have already discussed this in the first session. So what happens? It will be inverse of the equilibrium constant of the forward reaction, right? So the equilibrium constant for the reverse reaction or the backward reaction will be the equilibrium constant of the forward reaction, inverse of that. Okay, so I hope it is clear. As you can see, for the forward reaction it is Kc. Now for the backward reaction, that is Kc dash, it is 1 by Kc. Okay, so if you know the equilibrium constant for the forward reaction, we can calculate the equilibrium constant for the backward reaction by taking the inverse of it. It will be inverse of each other, right? Now moving on to the next one, if you are going to multiply the whole equation, okay, the whole equation we are going to multiply with any integer. Okay, so here we have taken n. That means to AA plus BB giving CC plus DD. To this whole equation I am going to multiply it with some integer n. Okay, some value n I am going to multiply. Now what will happen to the equilibrium constant? Earlier, before multiplying it, it was Kc, right? Now what will happen? Will it become n Kc? No, right, it will become Kc to the power n. Okay, so that is what is shown here, Kc double dash. That is, if we are multiplying it with any integer or any number n, what happens? That will come in the power. Okay, so if I am, for example, if I am multiplying it by 2, what happens? It becomes Kc to the power 2 or Kc square will be the value. So I hope it is clear. The equilibrium constant for forward and backward reaction are inverse of each other, and for if you are multiplying with the integer or any number, what happens? That will come to the power of it. So this relation is very important. Now moving on to the next one, that is applications of equilibrium constant. Okay, so the first one, it is used to predict the extent of reaction. To what extent the reaction can take place, we can predict it using by the value of the equilibrium constant. The next one is predict the direction of the reaction. That means whether the reaction is going to proceed in the forward direction or the backward direction, right? And the last one is it's used to calculate the equilibrium concentrations. Okay, so the first one is predict the extent of reaction. Okay, so let's see, equilibrium constant is directly proportional to the concentration of product and inversely proportional to the concentration of the reactants. That means that if the value of Kc, okay, that is the equilibrium constant is high, that means that the reaction is fast and it is almost near completion. That means if the value is higher, like 10 raised to 3, if the value of equilibrium constant is 10 raised to 3 and more, if the value is high, what happens? The reactions extent is towards the product side. That means it is almost in the near end of the completion of the reaction, right? That means the reaction is taking place fast, or most of the reactants have been already converted into products. So the concentration of the products is more. That indicates that the reaction is almost about to be completed, right? So now, but smaller the value of K, slower is the reaction and the reaction proceeds rarely. So we can say that if the value of the equilibrium constant is 10 raised to the power minus 3 or lesser than that, so that value is very less. In that case, we can say that the reaction is still in the beginning of the reaction. That means that the concentration of the reactants is really high. The reaction is continuing in a very slow pace and more of reactants are still present. That means that it still requires more time to complete the reaction, right? Or else we can say that the reaction is rarely happening. It is a very, very slow reaction. So just by knowing the value of Kc, we can predict this. Now, if the value of Kc is almost equal to 1, we can say that the reaction has attained equilibrium. So as you can see here, if it is negligible, that is less than 10 to the power minus 3, reaction hardly proceeds. It's a very, very slow reaction, right? And if it's equal to 1, both reactants and products are present at equilibrium. It has attained equilibrium, we can predict. Now, if it is extremely large, if 10 to the power 3 and more than that, if the value of Kc is that, then the reaction proceeds and almost it is ready to be completed. So just with the value of Kc, we can predict the extent of reaction, whether it is completed, whether it is going to start the reaction or it is rarely occurring, or is it at equilibrium, we can predict, right? Now moving on to the next one, predict the direction of the reaction. Okay, so it helps to predict the direction of the reaction at any stage by using reaction quotient. Okay, so this is a new term, QC, reaction quotient. So it's nothing different. It is quite similar with equilibrium constant itself. Equilibrium constant is a constant which we are defining at equilibrium, right? So reaction quotient and equilibrium constant is different in that way only. Equilibrium constant, we define it at equilibrium. Reaction quotient can be it at any other concentration. At any concentration, we can define reaction quotient. The reaction quotient is the ratio of product of concentration of the products to that of the reactants. It is same as that of equilibrium constant. Okay, it's same, except that the concentrations are not necessarily equilibrium values. So Kc will define only at equilibrium. What are the concentration of the reactants and products? We multiply that. That is concentration of the products raised to their powers, which is equal to their stoichiometric coefficients, divided by the product of the concentration of the reactants raised to the power, which is equal to their stoichiometric coefficients, right? So that is Kc. That is only at equilibrium concentration. And if it is not in equilibrium concentration, any other concentration, we can use the QC, which is called as reaction quotient, right? So now just by knowing the value of QC, how we can predict the direction of the reaction. If QC is greater than Kc, if reaction quotient is greater than Kc, the reaction will proceed to the left. That means reaction proceeds to the left means it will be in the backward reaction, reactant side. Okay, the reaction will proceed in the backward direction. If QC is less than Kc, that means Kc value is higher, the reaction will proceed to the right. That means it will proceed in the forward direction. Now, if QC and Kc are equal, of course, if they are equal, what does that mean? The reaction is it in equilibrium. That is rate of forward reaction and backward reaction will be equal. So, it is in equilibrium. So, just using the term of reaction quotient, okay, which is QC, which is exactly equal to equilibrium constant itself, but in any other concentration, right? So, if QC value is less, we can say that the reaction is in forward direction. If QC value is more than Kc, it is in backward direction, okay? Now, the last one, relationship between equilibrium constant, reaction quotient and Gibbs free energy, okay? So, what is Gibbs free energy? We have already studied in thermodynamics chapter. So, the relationship between delta G naught, that is standard Gibbs free energy, and Kp is given as delta G is equal to delta G0 plus RT ln Kc. So, this equation also we have studied in thermodynamics chapter, right? Delta G is equal to delta G naught plus RT ln Kc. Okay, where Kc is the equilibrium constant, delta G naught is standard Gibbs free energy, delta G is Gibbs free energy, R is universal gas constant, and T is temperature. So now we are going to find out a relationship between these, right? So at equilibrium, what happens? Delta G value will be equal to 0. At equilibrium, this term will be equal to 0. So how can I rearrange this equation and write, if this term is equal to 0, delta G naught will be equal to minus RT ln Kc, right? So at equilibrium, what happens? Delta G will be equal to 0 and Kc will be equal to Qc, right? We have already discussed this reaction quotient and Kc value will be equal at equilibrium. So how can I write the equation? Delta G naught will be equal to minus RT ln Qc. So instead of Kc, I can write Qc. So this is the relationship between delta G naught and Qc. Right, delta G naught is equal to minus RT ln Qc. Right, now if delta G naught is less than 1, Kc value will be greater than 1. It shows that the reaction is spontaneous, that is the reaction will take place. So the reaction proceeds in forward reaction and more quantity of the product is formed. It is proceeding in forward reaction means what? More amount of product will be formed. So that means if delta G value is less than 0, the reaction will be spontaneous, that is the reaction will take place and it will be in the forward direction, so more amount of product will be formed. Now if delta G value is greater than 0, that is it is positive. Here it is negative, right? Delta G naught value is negative. Here if it is positive, what happens? Kc value will be less than 1. It is negative, right? So Kc will be less than 1 and it shows that the reaction is non-spontaneous. Okay, so the reaction proceeds in forward direction and very minute quantity of products will be formed. So it is non-spontaneous. That means that if the delta G naught value is greater than 0, that means if it is positive and Kc value is less than 1, what happens? The reaction will be non-spontaneous. That means the reaction will not take place, right? And it will proceed in the forward reaction. That means that the amount of product formed will be very, very less. It is proceeding in the forward direction means reactants will be formed, right? Not products. So I hope that is clear for you. The relationship between Gibbs free energy and reaction quotient. Okay. So in the next session, we are going to discuss about the different factors affecting equilibrium. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.